This is lesson 2 of unit 4 on factoring. Today we're going to be factoring binomials. So by the end of this lesson, you should be able to factor a binomial and recognize some special factoring patterns. All right, so the first sheet that you got today was on the factoring thought process. Right now, what I want you to fill in is the very top box. Your first question you should ask yourself is there a GCF? After you've asked yourself, is there a GCF, you move on to your second question, which should be how many terms. In today's lesson, with how many terms, we're going to fully focus on when we have two terms. Another word for a two-term polynomial is a binomial. So today's focus is binomial. So make sure you fill that in on your factoring thought process. So let's get started on that. So at the top of the notes on our factoring binomials, you'll see when factoring, you always need to look for the GCF first, which is what was explained in our first video. So when we look for a GCF, or whenever we're factoring, we want to be on the lookout for special types of binomials. So after we factor out a GCF, we want to see, do we have ourselves a difference of squares? Okay, some people call it dots, difference of two squares. Okay, I just call it difference of squares. So let's remind ourselves of some examples of perfect squares. Remember, 1 squared is 1, so 1 is a perfect square. 2 squared is 4, so 4 is a perfect square. I'm going to list the rest of the perfect squares real quick. So 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49. You should know up to 15 squared, so feel free to pause the video and fill in the remainder. So there are the remainders of my perfect squares up through 15 squared. Be aware of those. Now let's talk examples of perfect squares when we're dealing with variables. Well, our first variable that we normally think of is an x. Well, that's not a perfect square, but when we square it, what's our first square with variables is x squared. Now, so that was x to the first power. Now we have x to the second power, and we want to square it. Power of a power rule says we multiply our exponents to get x to the fourth. Our next thing in line is x to the third, but we want to square it. 3 times 2 is 6, so it's x to the sixth. Together, so we got x to the fourth squared. Well, 4 times 2 is 8. And hopefully we're noticing the exponents on these perfect squares. All right, x squared, x to the fourth, x to the sixth, x to the eighth. We're going by even powers. So any even power is a perfect square. And that's good for us to know. So now let's look at the formula for a difference of squares. So here's the formula that's already filled in on your sheet. So this a squared means a times a, so it's a perfect square. B squared means b times b, again, a perfect square. And we have a difference of two squares. So whenever we have a difference of two squares, there's a formula. And I'll be saying this again and again, but this is how the formula goes. A, B, A, B, one's a plus and one's a minus. So let's go ahead and look at some examples. So our first example here, always ask yourself the question, is there a GCF first? So 16 and 9, there's no GCF other than 1, and that's not helpful. X squared and nothing, there's no GCF between them other than 1, and again, not helpful. So let's move on to our next step, which says how many terms? Well, how many terms do we have? We have 2. It's a binomial. So is it a difference of squares? Well, 16x squared. 4 times 4 gets us 16, and x times x gets us x squared. So yes, 16x squared is a perfect square, and our a value there is going to be 4x. Okay, for our 9 is also a perfect square because 3 times 3 gets you 9. So 3 and 3 gets you 9, so our b value is 3. Since we agreed it was a difference of squares, we're just going to set it up. It goes A, B, one's a plus and one's a minus, and we just literally fill in accordingly. So what was our a value? That was 4x. What was our b value? That was 3. No, you don't have to write the a and the b underneath in colors. I just wanted to show you how that works. This is fully factored because if you look at the first binomial, you have 4x and 3. Those can't break down any further other than 4 being 2 and 2, but there's no x squared there. It's not a difference of squares, and neither is 4x minus 3. So that's fully factored. Let's do some practice problems. I'm going to do the first one with you and then pause the video and try that third one on your own. So 2x squared minus 8. Is there a GCF? Yes, it's 2. Factor out your 2, and what's left? Well, you have an x squared minus 4. Now, the 2 is done. That's fully factored. Let's look at the x squared minus 4. That's a binomial. All right, x squared means x times x. So our a value is going to be x. 4 is 2 times 2. So our b value is going to be 2. Now, the 2 that was our GCF stays out front. Don't worry about it. You've already dealt with it. Remember your pattern. It goes A, B, A, B, one's a plus and one's a minus. And now we're fully factored. So pause the video, go ahead and take a look at the third example. So I showed you how to get from 81x to the fourth minus 1 to get 9x squared plus 1 and 9x squared minus 1. Now 9x squared plus 1, you'll notice that the 9x squared, that's a perfect square again because you have 3x times 3x. The 1 is also a perfect square because that's 1 times 1, but this is a sum, and we're going to find out next that sums can't go any further. However, our second one is another difference of squares. Since 3x times 3x gets us 9x squared, and 1 times 1 gets us 1, and there's a difference sign, we can go further. So 9x squared plus 1 is done. However, in our next one, we can break that down because we have an a value of 3x, and we have a b value of 1, and it's a difference. So how does it go? A, B, one's a plus and one's a minus. And now this is fully factored. So let's talk about a sum of squares. So our next thing is a sum of squares. Okay, sum of two squares. The good news is our formula, well, there really is no formula because a squared plus b squared is not factorable. We call it prime. So let's look at some examples. We have 100x squared plus 49. So is there a GCF other than 1? No, because 149 have no common factors other than 1, and that's not helpful. X squared and nothing, no common factors, not helpful. So they're perfect squares, but there's no GCF. So we have 10x and we have 10x. We have 7 times 7. So you think at first, oh, we have an a and a b. But if you were to factor this like normal, one's a plus and one's a minus, you would end up multiplying it out and getting a negative in the middle. Okay, this we need to recognize is a sum of squares. And for right now, we're going to say that's not factorable, and we're going to call it prime. Okay, it's not factorable. All right, if you look at the next two, for practice, you can pause me at any time, but x to the fourth and 1. Well, x to the fourth is a perfect square. And 1's a perfect square, but this is a sum of squares. Are sums of squares factorable? The answer is no, it is prime. Now, problem 2 in that section, is there a GCF other than 1? Yes, our GCF is 8. So we're not going to say prime right away. We're going to take out the 8. 32 divided by 8 is 4. 8 divided by 8 is 1, and we're left with an x squared left over. Now you'll notice we have a sum of squares, and we can't go any further because it's a sum of squares. So our fully factored answer should be this. Make sure you bring questions to class. I'll talk in another video about our rules for sum and difference of cubes.